Before I introduce the next discrete structure or data structure or object, I just wanted to mention to review, remember, strings are immutable, meaning they can't be changed, whereas the individual elements inside a list can be modified. Thus, lists are mutable. They can be changed. We can also explore why is it and how is it that lists and strings, which present the objects in sequence, we can explore how it's able to decipher between seemingly two of the same objects. Here we have an example of a list. It's list 1, and we know it's a list because we have the opening and closing brackets. Now we have blue, green, and red. Now below this we have more of a visual representation of a list. So as it is now, it's easy to see how the list is able to keep these objects straight inside the list because they are obviously different objects. Now, what happens if we add another object which looks the same, and how exactly would it differentiate between that object? So what I did in a very crude manner, I simply drew another green box to the best of my ability. I know I'm certainly no Van Gogh, but I hope you understand of what I'm getting at. I just simply drew another green box. And as you can see, I affected the list by simply adding another green box. And so if you, in this, let's pretend this is a new line right here. And what would happen if I said something like print list 1, and I said and I indexed the first position, which is this, obviously it would print this green box. However, if I said 3, it would print this green box. And even though they are essentially, it is seen as essentially the same, and I hope you understand that essentially I'm trying to make it look the same, the Python engine within the list discrete structure or data structure is able to differentiate between this green and that green. And how is it able to do it? Well, when a list is created, it doesn't only create the structure that you see here. It internally links each item or each element within the structure to a place, to an offset in the place of memory. Now, make no mistake about it. Other data structures that are different still have to reserve a place in memory, but it may not also reserve the offset, I guess you could say. So this is the 0 offset. That's the 1, 2, and 3. So this is how, when you say list 1 and you indicate that it's the third offset, that's how it's able to indicate it's able to run this green box. Because quite simply, this is, and let me see if I can use another color here to demonstrate it. This blue box is not just the blue box, it's this blue box and the pointer and the 0 offset. So this green box isn't just the green box, it is the green box plus the pointer and the first offset. This red box isn't just the red box. I hope you're understanding what I'm saying. And then finally, this green box isn't just the green box, it's the green box plus the pointer plus to this third offset. So you might be saying that's a lot of data, and frankly, you would be correct. What if you just wanted to create nothing more than just this list, and that's it? Fortunately, Python and all data languages have more than one collection or data structure that is dedicated to the concept of collection. The data structure called a set saves time and money and performance, I guess, potentially, by not linking an object to an offset in memory. Yes, the structure called a set does reserve a portion in memory for its structure in general, but does not take the time, effort, and expense of linking the actual object to an offset in memory. Consequently, you cannot have identical objects in the same structure because there would not be a way to differentiate them to make them unique, unlike a list or, for that matter, a string. Let's take a look at this example. As you can see, a set is quote unquote an unordered collection of unique items. So the fact that it's unordered and the fact that all of the items have to be different, thus they are unique, are kind of hand in hand with each other. Because if you had a duplicate of an item, like for example, a green box in the first position and a green box in the third position, a list as opposed to a set is able to differentiate them because there's a certain order or sequence in how a list treats its objects. A set, on the other hand, is kind of like a grocery bag in which there is no order to speak of. So because of that, because there's no system in place to order this collection, because there is no pointer to a place in the particular piece of memory for offset, then not only are they unordered, but they have to be unique because there could be no differentiation between them. So take a look at this. The name of this variable is lotto results, and this is your very first set. And we know it's a set because instead of the brackets, we have these open and closing curly braces. Now, where else have you seen the curly braces? Maybe when we were doing the print formatting, and also in other languages and perhaps in other classes or other knowledge bases. You may have seen these curly braces if you've ever done HTML and messed with cascading style sheets. But even if you haven't, just note that a set is a set. We know it's a set because it shows these curly braces right here. You know it's a set, but we have 3, 5, 8, 34, 3, 10. Just a collection of numbers. But you can see, I purposely built in the fact that we have a 3 here and a 3 there, and we press enter. Now there's not going to be an error. It just takes it in. However, if we said print lotto results, it's only going to print out the one of the number 3s, because quite simply, it only recognizes one of those 3s because there is no notion of a pointer to a particular offset. But you can go ahead and say index of 0, and you could try that, but guess what? A set object is not subscriptable. So in other words, it's calling this a subscript. So if this were a list, hey, you could have a subscript. And the other thing is there is no notion of an order. So you could say set 3, 5, 1 and is equal to, and notice there's two equal signs when we compare 1, 3, 5. And it's going to say that it is in fact equal because there is no notion of order. But if we created a list and we said 3, 5, 1, and that was comparatively equal to the list of 1, 3, 5, guess what? That is false because we're dealing with a list here, and we know this because we have these brackets as opposed to these curly braces. And again, if we said 3, 5, 1 was equal to each other, that of course we know that would be true. But if we said 3, 5, 1, 1, we would know that to be false. All right. So what purpose does a set or set logic really have in the real world besides saving processing power? One of the real world uses of a set is to remove duplicates, and they call it deduping. And we have a transaction ID here, and we've all seen transaction IDs on our receipts and things like that. So we have 451, 346. These are just random numbers I just generated or thought of. 234, 345, and then we have a duplicate 451. So imagine a list of maybe 100,000 transaction IDs, and you want to remove the duplicates or something like that. So in this case, how would we do that? So obviously this is a list, so we can change this list data structure to a set. How do we do that? We can say transaction ID is, oh, by the way, before I proceed, what I tried to do, and perhaps you understood this, is that in idle, you can type in the first part of a word and press tab, and if nothing else matches up, it will produce the one word that was used with that prefix. So here we have transaction, TRA, and I just press tab and the whole thing comes up. So that's one advantage of using idle. You would never use idle for serious programming or to hand in an assignment to me or something like that, or to hand in an assignment to one of your other professors, but it's good to try things out or to attempt at some programming with particular singular discrete structures, or as I said, to experiment. Anyways, so we have transaction ID, and when you say transaction ID, it recognizes this whole structure because we created a variable called with this list and we linked it to transaction ID as a word. So what we're going to do, so what knows about transaction ID, so we're going to say transaction ID equals, and this is how you create a set, and transaction ID. And now let's go ahead and print transaction ID, and it has the set value, but look, it took out the duplicates of 451. Now we can say that the transaction ID is equal to, get this, instead of saying set transaction ID, we're gonna turn it back into a list transaction ID. And if we go ahead and print it again, we will see that now it removed the duplicates and we're back to this being a list. So now we can say transaction ID dot append and yet another transaction ID, and we can print transaction ID again, and we have this new list. So in the case of 100,000 transactions and you don't want to have to go through each one manually and remove them, you could use a set. You can morph that data set into a set and then morph it back into a list.